Throughout this next unit, we are going to be looking at the progression of our understanding of the atom. In order to really start this lesson, we need to go back thousands of years, and we actually need to start our discussion with some philosophers. Now, these men were absolutely intelligent, they were absolutely great, but they're not considered scientists because they weren't actually doing experiments. What they were doing is what we would consider thought experiments. They thought a lot about what would make up our samples of matter, but they didn't actually quantify any experiments that would allow them to really create a scientific model. The people that we're talking about from thousands of years ago are Democritus and Aristotle. And back in the day, these two were actually fighting about what constituted matter and what really it was made up of. Democritus believed in a particle, which he called atomos. As you can see, that's where our idea of atom comes from. And in Democritus's brain, these atomos, these unbreakable particles, were like itty-bitty, teeny tiny pieces of the sample of matter we were looking at. So the story goes that he was walking along a beach and he thought, okay, the entire beach looks like one solid sample of matter. But then he scooped up a handful of sand and realized that the beach was actually made up of little itty-bitty particles of sand, which were fairly unbreakable. And at that point he thought, what if all of the matter that we have in the universe was similar to sand? What if all of the matter in the universe was made up of unbreakable, uncuttable particles that kind of resembled the matter that we were looking at, but just much, much, much smaller? Now, Aristotle did not believe in this idea of particles. He did not believe in atoms. Instead, Aristotle believed in the four elements. And that might sound good because we were using the term element, but these are not the elements that we are currently looking at. These are not things like hydrogen and oxygen. These were earth, fire, wind, and water. Aristotle believed in four elements, and he believed that varying proportions of these elements are what created the different properties of matter. So if something had more earth than air, then maybe it would be denser, it would fall down. If something had more air than water, maybe it would flow away. And if something had a little bit of fire in it, that's what Aristotle believed gave things life. So when you're talking about a bunny rabbit hopping through the field, Aristotle would look at that and say, oh, well, that bunny's got a little bit of life in him. He's got a little bit of fire. Now, today, thousands of years later, we understand that Democritus was actually much closer to a real understanding of matter. But for about 2,000 years, Aristotle was actually the person that most people believed. And that was because Aristotle had the backing of the church. That's like capital C church. That's like, don't argue with us or we'll throw you in jail. Just ask poor Galileo. After thousands of years, scientific discovery did eventually catch up in the field of chemistry and matter. And really, what we were looking at back then was the work of John Dalton, but also people like Proust and even Millikan, and really several others that worked with him. Dalton is the one that we're going to focus on because Dalton is the one that created our first atomic theory. And when we're talking about Dalton's atomic theory, we're talking about a scientific theory. This is not just an idea. This is not like Democritus and Aristotle's theories. A scientific theory has to have a lot of evidence to back it up. And Dalton's atomic theory had really four postulates. So initially he said all matter is composed of extremely small indestructible particles called atoms. Atoms of the same element are identical in terms of size, mass, and other properties. Atoms of elements of different are different. And atoms of different elements can chemically combine in order to create compounds. Chemical reactions can be thought of as a separation or a combination or really just a rearrangement of those atoms to form what we now know as molecules. Dalton's atomic theory, like all theories, was written to try to explain observations. And when we are explaining observations, what we're actually trying to kind of get our mind around are something called laws. You are going to be responsible for the early chemical laws. You're going to need to know what each law says, and you're going to need to know how to calculate different examples of each of these laws. So we have the law of conservation of mass, we have the law of definite proportions, we have the law of multiple proportions. And we're going to look at how each of these can be quantified, how each of these can be used with numbers in order to see how really, in science, a law is a summary of observations. So when we're talking about law of conservation of mass, law of definite proportions, and law of multiple proportions, we're really describing the observations. When we're talking about Dalton and his atomic theory, we're taking it a step further, and we're actually explaining why these occur. So let's take each law one at a time and look at an example of how we can quantify it. Our first law is the law of conservation of mass, and the law of conservation of mass states that in a chemical reaction, the mass of the products must be equal to the mass of the reactants. Remember, reactants, that's what we start with, that's what we react. Products, that's what we end with, that's what we produce. So when we're looking at an equation, we would write it as reactants yield products. And all this law is really saying is that however much mass you start with has to still be there in the end. So if we look at our first example here, during a chemical reaction, 5-gram sample of nitrogen is reacted with an 11-gram sample of oxygen. What is the final mass of the product of the chemical reaction? Which law do we rely on to solve this problem? You're going to notice in these law of conservation of mass problems, or law of conservation of matter, you're going to have different substances. So we're starting with nitrogen and oxygen, and we're having a chemical reaction in order to produce a compound that contains both the nitrogen and the oxygen. If you have different substances that are reacting and producing something else, then the problem you're looking at relies on the law of conservation of mass, or law of conservation of matter. So for this example, we said the law of conservation of matter told us that the mass of the reactants, that's 5 grams of nitrogen and 11.4 grams of oxygen, has to equal the mass of the products. 5 plus 11.4, 16.4, and I just rounded that to one place beyond the decimal. So what is the final mass of the product? 16.4 grams. What law allowed us to solve it? The law of conservation of matter. And what does that law actually say? During a chemical reaction, the total mass of the products has to equal the total mass of the reactants. And that's our first early law. Our second early law is the law of definite proportions. And the law of definite proportions states that a given compound always contains the same elements in the same proportions by mass. So the same compound has to have the same ratios when we look at their masses. So here we have a problem that says, in a second sample of the same compound that was produced, if it contains 8 grams of nitrogen, what is the mass of oxygen? Which law do we rely on to solve this problem? We know that this is going to be a definite proportions law because it's referring to the same compound as above. If you have more than one sample of the same compound, then the problem you're looking at is definite proportions. So in order to solve this problem, we just set up proportions, we set up ratios. So we know that our 5-gram sample of nitrogen reacted with 11.4 grams of oxygen. That same proportion, or that same ratio, has to be in our second sample. So now we have 8 grams of nitrogen, and we want to know how many grams of oxygen are going to be in that sample. And in order to solve, we can just cross multiply. So we have 5 grams times x equals 8 grams times 11.4 grams. So 5 grams times x equals 91.2, which would technically be grams squared. We divide both sides by 5 grams. And our final answer is 18.24 grams, or we would round that to 18.2 with the appropriate number of significant figures. Which law is it? Law of definite proportions. What does the law of definite proportions tell us? If you have the same compound, it has to contain the same elements in the same proportions. 5 to 11.4 is the same as 8 to 18.2. Our third law is the one that if people have issues, it's usually with the law of multiple proportions. And the law of multiple proportions states that if you have two elements that are going to form more than one compound, the different masses of one element that combine with the same mass of the other element have to be in a ratio of a small whole number. Now to simplify this, instead of same mass, I usually just think in terms of 1 gram. How much of the second element reacts with 1 gram of the first? And in order to simplify it a little bit further, I really focus on whole numbers in the end. I just keep dividing things and keep looking at different proportions until I find some that have a whole number relationship. So in order to look at this one, we're going to start with actually this same type of compound. But now we have a third sample. And our third sample contains 6 grams of nitrogen and 20.6 grams of oxygen. And we want to know if it's the same compound. Well, remember, in order to be the same compound, according to our law of definite proportions, the proportions would have to be the same for all three. So if you remember back, we had one sample that had 5 grams of nitrogen and 11.4 grams of oxygen. If I just figure out what that proportion is, it's a 0.439 relationship. Our second sample had 8 grams of nitrogen, and we solved that to be 18.2 grams of oxygen. That's also a 0.439 ratio. Our third sample is 6 grams of nitrogen and 20.6 grams of oxygen. If I solve for that, it's a 2:3:1 ratio. And because this is not the same as the other two, we know that these are not the same compounds. These two samples were the same compound. This sample is not. So then the last thing we need to do is actually figure out our small whole number ratio. And remember, in order to do that, I have to compare the amount of one element that reacts with the same amount of another element. Notice here I have 11.4 grams, 18.2 grams, and 20.6 grams. They're not all the same. 5 grams, 8 grams, 6 grams. They're not all the same. So I have to first figure out the proportion of how much of one of the elements reacts with 1 gram, or at least the same number of grams of the other. So for my example here, it says we're going to use 1 gram of nitrogen. And really the easiest way to do this is to think, okay, in our first sample, we had 11.4 grams of oxygen, and we had 5 grams of nitrogen. If I divide 11.4 by 5, that tells me I have 2.28 grams of nitrogen per gram of oxygen. I'm going to do that same thing with the new compound. 20.6 grams of oxygen per 6 grams of nitrogen. That tells me I have 3.43 grams of nitrogen per gram of oxygen. According to the law of multiple proportions, these numbers, the mass of one compared to the mass of the other, should be simple whole number ratios. Oops, and I just realized I wrote it right, but I said it wrong there. So let's just fix this. This was per gram of nitrogen per gram of oxygen, nitrogen. This is 3.43 grams of oxygen per gram of nitrogen. And now I'm just going to compare these guys. So really the question is, if I have 2.28 and 3.43, what ratio is that? And in order to figure that out, I can just divide them each by the smaller number, and that gets me a 1 to 1.5 ratio. And you might stop there and say, oh, but wait, this was supposed to be whole number, and it's not. But luckily, you guys know enough about decimals at this point that you can look at that 0.5 and say, oh, that represents a half. Whatever decimals you wind up with should be very recognizable. They should either be quarters, thirds, or halves. And at that point, you multiply both numbers by the denominator. So if we multiply this by 2, we now get a 2 to 3 ratio, which is the small whole number ratio that was referred to in the law of multiple proportions. So again, you're responsible for knowing each of the 3 laws. You're responsible for knowing how we can use these type of calculations to show each of the 3 laws. And you're also supposed to know Dalton's atomic theory. And remember, because this is a theory and these were laws, the idea is that our theory should explain why our laws are what they are. So for instance, because Dalton thought of these as indestructible, that means that their mass is always conserved. Even if we combine or separate or rearrange the atoms that were there in the end are there in the beginning, the atoms that were there in the beginning are there in the end, so the mass can't change. And because all we do is take these different elements and combine them in ratios in order to make each compound, the definite proportions of the masses will always be the same because it's always going to be the same ratio of atoms. Keep in mind that there are some minor tweaks to Dalton's atomic theory based on our modern understanding of the atom. And really what we would have to do is we would either have to get rid of the word indestructible, or we would have to say that they're indestructible in chemical changes. Remember, we can actually break apart atoms in nuclear changes. And we would also probably get rid of the words like mass and size here, because now we know that there are things like ions and isotopes that might differ slightly from one atom to another atom of the same element. We would probably just refer to the atomic number or the number of protons when we're talking about what's identical. 3 and 4, pretty much still the same though. So one more time, you should be able to tell me the difference between Democritus and Aristotle. You should be able to tell me how for thousands of years we were looking at philosophers, and then really hundreds of years ago we jumped to scientists. You should be able to describe the postulates of Dalton's atomic theory, and you should be able to describe and apply each of the early laws. If you have any questions or if you struggle to do any of those objectives, please let me know and we can go through these things one more time.